floor is yours.
Thank you. Good morning. Um, okay. So my name is Ntabi Singh. I think he didn't want to try to pronounce that one, but my name is Ntabi Singh, and I am a student at the University of South Africa. I'm doing my master's, and my supervisor is here with me, Professor Kaitano. So my other supervisor could not join us, Professor Kevin could not join us, and I'm going to be doing a presentation on fog and global aviation, the state of knowledge evolution. So weather and meteorology are critical components of daily life, and weather basically informs what we do, especially when it comes to outdoor activities such as tourism. We rely a lot on weather. If you decide to move from here to go to another place, weather will inform if you stick to your plans or if you actually have to change them. You can't just wake up and decide to go hiking, for example, if the weather is not friendly. So in aviation, weather and climate are critical considerations because aviation will also depend a lot on weather. And because of this, it's important for pilots to understand the weather so that they come up with preemptive measures. And one key weather parameter of interest to airports is actually fog. And this is because fog can be very disruptive. And fog can pose safety risks and disturb airport activities. Aircrafts can be delayed, they can be cancelled as a result of fog. And like I've already mentioned, fog is very important for aviation stakeholders such as your airport managers, pilots alike, aeronautical service providers, because it impairs visibility, it makes landing difficult. We have also seen cases even in South Africa where aircraft get redirected because of impaired visibility as a result of fog. And yes, so aircraft get redirected. And we also have instances or situations where fog actually causes material damage to the aircraft themselves. And we also experience delays and cancellations as a result of fog and aircraft. There's been lots of documented cases of aircraft accidents as a result of fog, which reduces visibility. So the aim of this paper is to map academic interest in fog conditions and global aviation so that we determine the trends and the debates surrounding this fog. And the objectives were basically, like I've already said, to analyze the academic trend in fog and aviation-related material, to also understand the evolution of themes and fog and aviation. And you will see this in the next few slides, how thematic issues have been changing over time. And to also understand the evolving debate around topical aviation issues over the years, the impacts of fog on aviation, as well as fog reduction measures. So the methodology that we used, a bibliometric analysis of all Scopus index material. So basically, we were looking at, we were using Scopus, which is a trusted scientific database. We used it to, so Scopus has 2.4, it's quite a trustworthy site, like I've already said. It has 2.4 billion cited references, more than 94 million records. And so to search for the articles that we wanted, we used the term fog airports, which yielded 487 research articles that were published between 1928 and July 2024. And in order to analyze the results, we were using Scopus analysis tool as well as Force Viewer software. And these are the key findings from the 487 articles that we were able to get. So there's been an exponential growth post-1990 from about an average of 5 articles per year to between 20 and 30 in 2018. And the reason for this is you'll find that post-1990, or most of the times, I'll give an example with a presentation that we had yesterday that spoke about revenge tourism. You'll find that most of our research is actually reactive. Something has to happen for people to focus more. So that is the case here. You'll find that around 1990, the reason why there was an exponential growth from there is because there was actually an accident in China where it was about 3 aircrafts that collided. And then the same thing here in 2018 that explains the growth that went from between 20 to 30 articles in 2008. This is because in a space of 5 months there were 2 accidents that killed over 500 people, which was quite a lot because in 2017 only about less than 50 people died due to aircraft accidents, but in 2018 over 500 people died. So around that time, generally you'll expect scholars and people to get interested in wanting to understand the field more. And another key finding is that most of the studies that were retrieved from Scopus were actually concentrated on countries such as the USA, India, China, Canada, Germany, and the UK. So there seems to be a great geographical gap in terms of which areas focus more on publishing. And another thing that we're also realizing is that how fog really affects aviation is not fully understood. And like I just mentioned, there are quite great geographical gaps. And this is also because the areas that are choosing to do research have quite great international aviation hubs compared to the others. And a failure to address these gaps will actually result in economic and human casualties. And air traffic controllers will also encounter significant challenges if we don't really understand how fog affects airports and aviation in general. And then another great finding is that we are seeing that there have been thematic concentrations that have evolved with respect to aviation and fog. So you'll see the diagram in just 2 slides. Before 2005, a lot of the research was focused on understanding the interface between aircraft operations under fog conditions. Some of the research was also focused on understanding landing systems, since especially for airports that are not as technologically advanced. And some of the research was also focused on understanding how aerosols near airports contribute to foggy conditions. And then between 2010 and 2015, the role of forecasting in dealing with challenges of fog at different airports was also topical. And this is because, like I've already said, aviation relies a lot on weather. So it's important to understand how forecasting can be improved so that pilots are also at ease when flying. And then the impact of fog at various international airports was also studied, although this was also biased because it was mostly focused on international airports. Again, speaking to the issue of geographical gaps. And other studies also looked at how optical radar and radar imaging can be used to enhance safety and efficiency, because a lot of our aviation meteorologists depend a lot on radar technology because it enhances they are able to use it to predict visibility and fog. And runway visibility was also a major concern in this period. And this is the diagram that I'm basically speaking to. You will see that there has been an evolution in terms of what issues scholars have focused on over the years. But what remains a key issue is how fog affects or impairs visibility. And then I'm going to go back to the diagram again. So towards the pandemic and post the pandemic, what we are seeing is there's an interest in machine learning, deep learning, as well as fog computing. So most research is now focused on how to better predict fog. And this period also marks the deployment of the Internet of Things and the effect of fog on airport security is also being explored during this very period. And then in conclusion, we were basically looking at the evolution of fog at various airports worldwide. And the reason why we are doing this is because we understand the importance of improving passenger safety so that we also minimize the costs and the losses, including human lives associated with this. And we also come to the conclusion that there is a need to find a solution for this challenge. And I forgot to mention that this is actually part of my master's qualification here. I'm currently busy with my master's, so this is part of it, and thank you.
Thank you very much. Do we have any questions from the audience? Yes, gentleman on the line.
Hi, good morning. That was an insightful presentation. My name is Enoch from Kingston University in London. My question has to do with your methodology. So you said you chose Scopus because it's a trusted academic database. I mean, someone might also say there could have been other papers published in Science Direct, in EBSCO, and what have you. And the scope of your sample might really affect the generalizability of the findings you presented. So maybe just a thought in justifying why you are using maybe Scopus as a database. Just saying it is a trusted academic source is not enough. Probably it has a lot of journals that are related to airports, aviation, or what have you. I think if you do that extension of justification, it becomes more understandable by just saying it's a database. And again, I don't know whether I didn't see it. It would have been interesting to see the groupings of the research journals to know which journals really had a dense concentration on some of these articles you found, because it helps, especially when it comes to segmentations of which journal produced which papers and what have you.
Okay, thank you. I didn't hear a question, but your comment is noted. Thank you very much.
Any other questions?
Yeah, so I think what I understood that I think the fog is a solved issue because most of the aircraft, they rely on the instrument. Okay, so, and as a civil aviation body job is to regulate if that aircraft is equipped with the proper instrument, whether they can land in this specific airport or no. So I don't see what's the issue in the fog. While most of the aircraft are equipped with instruments that can like land and take off near zero visibility. So what are we exactly looking for here? Thank you.
Prof. Dube, do you want to respond?
Thank you, but I think that was more of a comment. Safe to say, I think the biggest reason why fog becomes a matter, even though we have got, I think, instruments that are able to, in some instances, to actually land near zero visibility. You would also understand that across the length and breadth of the
Okay, thank you for your presentation. That's really interesting. A couple of responses to some of the questions. One of the biggest issues of fog is the ability to forecast fog, or the inability to forecast fog in aviation. So there are many scenarios, for example, in the UK, where the local weather forecasting agency will predict fog the night before. So at 10 o'clock in the evening, you have fog predicted for 6 o'clock the next morning. And then 6 o'clock, then at 10 o'clock, what happens is that the airlines will start cancelling flights because of fog. And then at 6 o'clock in the morning, there is no fog. So you end up in a situation where you've cancelled lots of flights and unnecessarily. Or the other way around, you have no fog forecast, and then at 6 o'clock in the morning, you start cancelling flights, but passengers are already on their way to the airport, and so it's too late. So the main impact of fog is airline operations, because you are expected to implement low visibility procedures, LVPs, at airports. So the spacing between aircraft during taxiing has to increase, between landing has to increase, and that reduces the flow rate, and that's the challenge. My question was on, if you remember back to the presentation by Professor Williams yesterday, he was talking about the impact of climate change on aviation. And we looked at data for fog occurrence in London, and actually over the last 30 years, the fog occurrence is reduced, which is a benefit of climate change on aviation. So my question was, have you, in the papers that you reviewed, were there many papers that looked at the long-term climatology of fog?
Okay, thank you for your question. So, with fog in climate change, there are actually mixed views about that. There are some scholars who are arguing that in the long run, we will see a decrease in fog, whereas in some spheres there will be an increase. So it's, yeah, it's a bit of both. I do have that, actually, we do have that on the paper that's been printed, actually, so yeah.
Okay, I think there's a great opportunity to look at observed data at airports, because there is a long record of weather recorded at an airport for many airports around the world, and I think it would be very easy to trend that over time. So I think there's a good opportunity for further research there.
All right, thank you.
If you could join me in thanking our speaker one last time. Okay, is our next speaker ready? Yep. I'll give the mic. It's top button, right? It's too small. Can you use the point to the mouse pad? I'll do the instructions then. I'll give it to you. Okay. Okay, everyone. Thank you again. So we have our next speaker from Emirates Aviation University, Mr. Hussein. I love the name because it's the same as mine. So I think this is going to be a really good talk. So the floor is yours.
Thank you. Good morning, everyone. My name is Rashid Hussein. I am a mechanical engineer from Dubai Police, the General Department of Airport Security. Today, I'm going to present to you our topic, which is the analysis of the supralloy that is used to manufacture the turbine blades and the thermal barrier coating to develop them to withstand the higher temperatures. Our headlines are going to have introductions, the methodology with the subtopics, which is the model geometry, the model setup, the static structure analysis, and the thermal analysis. And then we'll move to the blades materials analysis, which will include the blade analysis without thermal barrier coating, and then the static structure, the steady state thermal analysis, and then we'll have a summary of the performance of the uncoated blade. Finally, we'll have the summarization and the optimum thickness analysis. To start with, gas turbines is a turbomachinery device that operates on Brayton cycle. is a device that shifts the energy of the fuel into shaft work or even a thrust. Gas turbine engines, when you compare them to any conventional engines that both generate the same rate of energy, gas turbine engines can come in a smaller size. Not to mention that there are far less vibrations and smoother shaft rotation, which will make them desirable in the aerospace applications. Gas turbines operate at a very high temperatures ranges of about 1,200 up to 1,500. Gas turbine blade materials require additional cautions to withstand high temperatures. In general, the turbine blades, you can see the gas turbine engine. It consists of 4 sections: the intake, the compression, the combustion, the exhaust. The turbine blades usually comes directly after the combustion engine, which directly have the impact of the hot gases, which will rise its temperature up to 1,500. To manufacture the turbine blades, they need to be manufactured of a superalloys. Now, nickel-based superalloys are favorable for such a design. They have a high tensile strength, high fatigue, high creep, and they can withstand the high temperatures. In order to cool them down, a conventional method, which is to cool the turbine blades, is to extract a fraction of the air that is coming from the compressor of the engine to cool down the turbine blades. However, a new perspective has been suggested recently by the ceramic researchers. Thin layers of a certain coating ceramic materials is applied onto the blade surface as a thermal barrier coating goes by TBC, is another alternative. Thermal barrier coating is a multi-layer composed of a ceramic top coat, a metallic bond coat, and a layer between them, which goes thermally ground oxide. In figure 2, you will see the 3 layers. The bond coat, which comes directly after the surface of the superalloy, the thermal ground oxide, and then we have the thermal barrier coating, which goes from 2 micrometer up to 300 micrometer. The decreased heat through the thermal barrier coating is controlled by the thickness and the thermal conductivity of these layers. The heat insulation is enhanced through increasing the top coat layer thickness. As you can imagine, if we apply the thermal barrier coating on the turbine planes, it definitely would decrease its temperature. And by that, we can ensure that this turbine will operate within the safety limits. However, we cannot increase it as much as we want, as might someone suggest. There should be always a limitation to our design and our thickness. For example, if we increase the top coat layer, it will cause a potential thermal mistress. This mistress will lead to cracks in the blade itself. So a balance should be taken into consideration. We'll move now to the methodology. In the methodology, we use a software called ANSYS. It's a software that's used for simulation for mechanical and thermal analysis. A model was cleaned up and grid was generated through ANSYS Mechanical. Element size varied up to 2 millimeters to properly capture the structure and thermal behavior. As you can see in figure 3, these small elements, the smaller they get, the better result we will have. These small elements will help us to capture an accurate results for the simulation. Of course, you are limited by the computational power that you have already. Mesh quality was average value of 0.85. It means how stable and accurate result we will have. Usually a 0.85, starting from 0.85 and up, will ensure us an accurate results. Now we move to the first part, which is the static structure analysis. The root of the blade was set to fixed support. As you can see in figure 4, that the base of the blade itself is fixed to the turbine disc. So in order to fix it, we assign it to be fixed in its place to ensure no movements in any of the 3D directions. The whole simply spins at extremely high speed, which induced a centrifugal force due to the rotation, up to 10,000 RPM. In figure 5, of course, the turbine in its surface, it will rotate up to 10,000 RPM. So we had to include it in our simulation. This centrifugal force will cause a deformation. The hot gases impact from the compressor induce a high load of 980 Newton, which is applied to the plates. Figure 6 is show you where this 980 Newton are applied. Of course, this hot gases will impact, on the other hand, as much as the centrifugal forces. The boundary condition and loads. Due to the fuel burning process in the combustion chamber, extremely high temperature hot gases flowing over the plate surface of 1200, as we mentioned before. The disk rim temperature is considered high as well, and higher than the inner parts of the disk, which cause thermal stress to occur. To mitigate the thermal stresses, a relatively low temperature air is passing on the disk face, which was extracted from the compressor, as we mentioned. Here in figure 7, we assigned the surface of the plate, the upper surface, up 1200, which will capture the high temperature that's coming from the hot air stream. But in figure 8, the base of the plate was assigned 650 since its temperature is lower than the upper face. Plate analysis without that thermal barrier coating. Following the recommendation of various researchers, Incolin 718, IN625, and RENE41 were selected for their exceptional properties. The blade was first analyzed without the thermal barrier coating for static structure, and the results of the total deformation, the equivalent strength, were noted. Moreover, a steady-state thermal study was also conducted. First of all, for the static structure analysis, here we have on the left side for the total deformation for the Incolin 625. As you can see on the right hand also, we have the RENE41. It's another superalloy material. After we applied the boundary conditions, we will notice that on the tip, on the plate itself, you can see that there's a deformation of 1.8 millimeter. However, for RNE41, you will notice 2.2, which is higher than the Incolin 625. Here it shows you that the Incolin 625 has a superior properties in terms of the total deformation, and it can withstand higher than the RNE41. Now for the equivalent stress, on the left side you have also the Incolin 625, and on the right side RNE41. As you can imagine, the maximum, the high stress occurs at the tip, at the middle of the plate. And you can expect that since the base of the plate is fixed at the disk rim, while you have the upper half of the plate is free to move. And both of them, they show the high stress at the same location. But notice that in the Incolin 625, it has a 10,500 megapascal. On the other hand, you have RANE41, 20,000, which almost the double. That tells you that the Incolin 625 can withstand a higher stress, and it will be safer for application. Now for the steady-state thermal analysis. After the static analysis, we have the thermal analysis. The comparative analysis showed that IN718 is to be selected for high temperatures application among the tested materials. You can notice that in figure 11 on the left side, you have the Incolin 718. The highest temperature that was captured was 1,155. On the other hand, you have the RENE41, 1,186. However, the high temperature of the exposure, which is so close to the melting points, could lead to the turbine failure. So to extend the plate surface life, a proper coating for the plate surface must be applied. The next table is summarization for the steady state for the turbine plate, but without the thermal barrier coating. Here you have, notice that none of the three materials showed a superiority in terms of the tested parameters, since they all varied. But you can notice that Incolin 718 showed a significant improvement comparing to the other materials in terms of temperature and equivalent stress. That's why Inculin 718, it will be selected to be applied as a turbine plate material and to be moved to the next step where a thermal barrier coating will be applied. The coating material should possess a lower thermal conductivity in addition to a low density. If the thermal barrier coating weight is heavy, this will cause the turbine to require more power to run and the reduction engine of efficiency as well. A coating material named yttrium stabilized zirconia has been considered. The next table, it shows you the properties of this material, coating material, which will be applied as a coating material for the turbine plates. This material is widely suggested by researchers as a coating for many other applications, not just for the aerodynamics. Notice that the zirconia itself is a material that always used as a coating material. In a nuclear reactor, zirconium nitride is used as an insulation for heat to isolate the nuclear fuel from the surroundings. After we applied the thermal barrier coating on the blade itself, the Inculin 718, we applied a several thickness for the coating, which is summarized in table 3. Please notice that we applied 100 micrometer up to 900. Those are chosen results. You will notice that the more we increase thickness, the temperature will decrease, and we can see a significant decrease in temperature, which proves that the coating material is isolating the heat due to its lower heat conductivity. In this plot, it shows you that for various thicknesses from 100 to up to 900, the temperature will start to decrease, and then it will slightly increase at the end. However, there is the black plot, it shows you the cost. Now, in order to choose the optimal thickness for the coating, we made an intersection point between the cost and the temperature, and intersect at 550 micrometers. To conclude our presentation, a computational analysis was carried out on a gas turbine engine plate from a structural and thermal perspective with mechanical and thermal loads. Without coating, 3 candidates for blade material were compared: the Inculin 715, the Inculin 625, and the RANE 41. Among them, Inculin 715 considered the best suitable material due to it can withstand the higher temperatures and have a higher melting point among the others. A steady-state thermal analysis was held, which yttrium stabilized zirconium thermal barrier coating was used at various thicknesses. Optimum thicknesses of 450 micrometer was recommended. A considered future work regarding the vibration analysis will take place. Notice that yttrium stabilized zirconium is not the only coating material. There are various coating materials, and this is the beauty of it. You can apply any coating material, you can simulate it, and you can see for yourself which one will give you the better results. And those are for references. Thank you for listening.
This is very too technical for me. So
Yeah.
basically, what is this? In simple words.
In a simple words,
Coating, is it a coating that,
coding,
coating.
it's about a coating material
Yeah.
that we can apply to the turbine plates of the aircraft. You see the turbine plates, they are facing the highest temperature in the whole engine. And so we have to insulate them to ensure they are protected against the heat and the oxidations, erosions. So we need to cover them up with some material that will lower the heat conductivity, and they will give them a longer surface life.
Okay.
So they are
So-
protection.
So basically, it's a material that helps the turbine engine to, like, I don't know, last longer and
Exactly.
can handle harsher conditions.
It's just like when you are wearing a jacket in winter
Okay, okay. Nicely simplified. As an airline, uh, is it cost effective? Like, why should an airline add this coating?
Uh, from a safety perspective, of course, and from maintenance perspective, we need to ensure these blades will have a longer surface life. Of course, replacing them will cost a lot of money, not to mention failures or incidents that we are trying to avoid in the first place. Of course, as I mentioned before, if we just add as much thickness we want, this will make the turbine blades weight much, much higher. And you can imagine how much a turbine have blades around it. So that's why we made this optimum thickness study to ensure that there's a limitation, there's a certain thickness that no need to exceed it, and it will do the full job.
Okay, thank you.
And to ensure that the weight is not too high.
Okay, thank you.
Can I ask a really quick question?
Please.
Did you do a mesh sensitivity analysis when you arrived at that 2 millimeter sort of mesh size?
For the mesh study, the mesh were repeated many times. Of course, the smaller you go in mesh, you will need a much computational power.
And it doesn't mean you get accurate results. So that's
Exactly, but you still have to ensure that beyond this size, it's enough to continue with the simulation. But however, in this presentation, we focused mainly on the results of the turbine blades. And the mesh analysis was conducted early. But it shows that the 2 millimeters was enough to capture the thermal and mechanical results. Thank you.
Actually, the grid independence test was done. As you know, there is a coarse, medium, and fine mesh. And after that, you will see, you will get the relative error. And based on that, you will select the best mesh that you need. Actually, this study was done, and what Mr. Hussein is presenting is the medium level, which is considered a grid independent. So based on that, he is presenting these results.
Did you do any validation of your simulations against any? I know it's difficult to find data for these conditions.
Experimental validation. Actually, this will become like a future work. In this conference, we decided to make it like a numerical presentation, and this will be like a future work to hopefully to make experimental comparison with what we have. Yeah.
If we don't have any questions, then can we thank our speaker again one last time? Thank you. So, can we have our final speaker, please? If they're here. Yes? No? Mr. Al-Hamamdi? No? Wait a little bit. I thought it was so discreet. Hey. Okay, we have our final speaker ready?
Yes. Can we go over
Yes.
use a board or something to present some calculations?
Yeah, I guess so. Yeah. You want to use your laptop?
Kind of like a laptop, like board here or something.
I don't think we have anything to show. Do we have anything to do any calculations? The
Like a board here or something.
whiteboard?
Whiteboard.
Cool. With the one in the corner? Will that work? Yeah? Yeah. Can we get down here in the corner? Yeah? Don't make it too complicated so I can't follow. Okay?
Yeah. Just
It's
simple
like
one.
simple calculations.
Yeah, just simple calculations. I already also prepared the results. Like I mean,
Okay, sure.
no need to do it. No need to do like physical.
Okay, good. Okay, this is going to be really good. It's going to be worth the wait, I promise.
Good morning, everyone. Our distinguished guests, ladies and gentlemen. My name is Fas Labib Hamadi. Today we'll talk about the what is the this one. Thank you. Yeah. Okay. So my topic today is to talk about the factors that can affect the reliability of the aircraft operations, such as its systems and components. So first of all, I want to define the reliability is simply to make sure that the component or the system is doing its intended functions within a certain life period under certain conditions. If yes, then you can say that this component is reliable. So as you know, the field of aviation contributes $3.5 trillions towards the GDP of the world. Usually now most of the people, they are traveling using the aircrafts. And the reliability of the flight operation does not only depend on any single factor, it can be addressed by following the multi-pronged strategy. For example, the personnel, the ATC, the MROs, the quality controls, the training departments. All these departments are all just a simple aspects of the factors that can affect the reliability of the aircraft. So in our research background, we have addressed some of the factors in our research paper. So first we will start our topic today with the relationship between the reliability time and failure rate. Then we will go to the maintenance-related mandatory occurrence reports, maintenance versus time downtime, experience-related incidents, supply chain and economic stability, climate and weather conditions, human factors such as the pilot, air traffic control, personnel, air traffic management, quality control. All these are factors that can affect our reliability of the components. These are just a few factors. However, there are furthermore to be discussed. So first of all, I want to mention that there are nowadays recently there have been a great, as you know, there was like an enhancement in the methods of the maintenance. So recently they are using the RCM, which is the reliability centered maintenance, is a proactive maintenance strategy aimed at optimizing the reliability and performance of assets while minimizing its cost, which means that I will use the best and the most suitable maintenance strategy for each of the components, such as if we have a light bulbs in the aircrafts, I will not do a preventive or a predictive maintenance strategy. In other hands, I will do a reactive maintenance strategy. But if I am using the engines or the igniters of the engines, then in this case, I will be using the preventive or the predictive maintenance strategy, which will cost a little further more, but it is more suited for this kind of critical parts of the aircrafts. So of course, these advantages will give us more reliability and increase the, like for example, increase the enhanced reliability of the components from its starting used or serviceable timeline until its wear out zone. Of course, it will lower the cost furthermore in the future, and it will be more efficient for our maintenance program. So first, he will do some calculations. So first of all, I want to introduce you to the reliability equation at a given time, which is R equal to the exponential lambda times T, in which lambda is the failure rate and R is the reliability. So now, in order to calculate the failure rate, we need to know three things. First of all, we need to know that the NF, which is the number of the failing components at time T. Then we need to know the number of the live functioning or serviceable components. And at the end, we need to know the number of the live components at time 0. So let's say, for example, can everyone see the board? Okay. So let's say, for example, a manufacturing company has produced 2,000 aircraft, okay, distributed to the owners, okay. Then let's say after a period of 2 years, 250 of these specified type of aircrafts has been having a failure rate. So what I mean by failure, it has been failed. So it has to be inspected. So in this case, I will use this simple formula. Actually, I have already written the results just to not waste your time, ladies and gentlemen. So simply, I will just do like this, 250, which is the number of the aircrafts, divided by 2,000 times the time period, which is 2 years, which will give you a failure rate of 0.0625 per year. course, this can be like a little number, but of course, I'm talking only 1 year. So accumulated, as you know, the aircrafts can be like 20, 30 years being used. So after 10 years, this will be like a really bad trouble to the commercial organizations. So now, if I want to calculate the reliability of this specified type of aircraft, I will use this formula, which is R is equal to exponential lambda times T. So now, as we say, the failure rate is 0.0625. This only bear 1 year, and the time that we have is 2 years. So we will take a reliability of 0.88, which is equal to 88%. So in only the first year, this type of aircraft has a reliability of 88%, which is of course a bad reliability. So we can also calculate. So okay, can you hear me like this? Yeah, it's better for me because.
Just so they can hear you online.
Okay, cell same. Okay. Okay. So this is the graph that I previously explained, which says that for any component, of course, there is some of the early failures. These early failures can be just due to the design process or the manufacturing process. This is the usual one, which will be low at the start of the servicing of the part itself when it is installed on the aircraft. However, at the end of the serviceable period of the component, we will have the wear out zone, which can be wear out failures due to the, let's say, due to corrosion or due to creep or due to any other deformation or defects. So our purpose is to decrease this exponential graph and make the wear out failures to occur later on the components and on the aircrafts. So we came to the conclusion also that we have two types of, actually there are three, but here I will just explain about two. The third one is in our research paper, just to not consume your time. So here we have reliability in series and reliability in parallel. So we found out that if the components of the aircrafts are connected in series, it will be a bad idea. But however, if it is connected in parallel, it will be a better idea. And we will see now why. For reliability of systems connected in series, we can just use this simple formula. Let's say, for example, let's take, this is our reliability of the aircraft, okay, 88%. So now, let's consider this aircraft as a component. And let's say that these two components are connected in series. So in this case, I will just have to do 0.88 times 0.88 for component A and component B. This will give me a result of 0.77, which is equal to 77 reliability. So the unreliability of this component is simply 23%. So as you recognize here, when I'm connecting the component in series, the overall reliability of the system will be decreasing less than the single reliability or the individual reliability of the component itself. However, let's take another example in components that are connected in parallel. So now for the components that are connected in parallel, we will use another formula. Of course, Q is the unreliability of the component. So let's say the same component, and we will just simulate the equation times Q, which is 1 minus 0.88, okay, So as you can see here, when I'm connecting the same components, but just in a different method, which is a parallel method, we get a reliability of 99%. So we came to the conclusion that connecting the components in a parallel will give you a overall reliability more than each of the individual components. Here also you'll find a simple graph. As you can see, these two graphs, this one is for the series and this one for the parallel. For the series, as you see, the more the number of the components, the less the reliability. However, in the parallel, the more the number of the components, the more the reliable will be the system. Of course, I know that some of the components cannot be connected in series, but however, if we can connect as more components in parallel, or as we are using the third system, which is combined parallel and series system, our aircraft will become more reliable and our system becomes more reliable. So now the second topic is the maintenance-related mandatory occurrence reports. As you can see here, the aircraft software system, as you know, helps manage and track compliance, ensuring safety standards are met. However, we make a study and we found out that ATA Chapter 25, which is the equipment and furnishing, has been like has accumulated most of the unreliability components. And secondly will be the ATA Chapter 71 to 80, which is the power plants, the exhaust, the engine. So our idea is to focus more on these two sections of the aircraft in order to increase the reliability of the aircraft. So then we will go to the maintenance and versus downtime. Of course, no one of the organizations wants the downtime to be high. Everyone wants to be low. So we made a study that the cost associated with the aircraft, of course, the reliability will make the maintenance cost reduced, the operation efficiency also will reduce, and the reputation. So in this study, as you can see here, in October and in February, the revenue was high. But however, in the others was low due to the high downtime of the aircraft and its components. And this all related, of course, to the reliability. Experience-related maintenance incidents. As you know, we are human. Incidents happens everywhere, not only in aviation. But before a couple of years, I have read one of the great books in which it has a graph saying that before and the early invention of the aircrafts, the human error was only 20%, and the errors due to the machinery and due to the systems was 80%. However, recently nowadays, the human errors has been totally swapped and become to 80%, which is the human factors, and only 20% is related to the technology and system-wise, which means we are, as a human, we should train ourselves professionally to make sure that this 80% has to be decreased more and more. And also we have to learn about these technologies in order to enhance and preserve our reliability system. Now, one of the largest factor that can contribute and affect the reliability is the supply chain. Supply chain is like a big sea, you know. It's like starting from the product coming from the organization until it has been delivered to our customers. This will include, of course, the storing, the handling of the component, the packaging of the component until it has to be installed on the aircraft. So we as technicians and engineers, we have to make sure that these components has been taking care of it from the first stage until it has been installed on the aircraft. This only just to reserve the reliability of the aircraft as we have received it from the manufacturing organizations. So as you know, the aviation supply chain management with significant efficiency, reliability, and competitiveness. The challenge, of course, the globalization and the regulatory compliance. But however, we can comply with the regulatory and we can adhere ourselves to, we can make ourselves to at least compete with the globalization and do what they are doing. Okay. Last but not last one is the economic stability. Last factor is the economic stability. Of course, economic stability will have a significant influence on the aircraft reliability through various factors. However, this economic stability can be maintained by the collaboration, adoption of technology, and the risk management. And these all are being done by the personnel. Okay. Now, the last one it is the climate and weather. Here in UAE, we have like hot weather most of the time. So we have to take this into consideration that some of the bars that we are taking from other countries, it has to be under our climate and weather standards, and we have to make sure that they are monitored properly, especially the critical parts. And for example, if you have extreme temperatures, can affect the viscosity of the fluids, such as the engine oil and the hydraulic fluids, potentially leading to increased friction and reduce its efficiency. So we have to take this into consideration and reserve the reliability of these kind of fluids before it can reach to its failure wear out zone. So flight controls, of course, these flight controls, such as the aileron, the elevators, the rudders, these are critical parts of the aircraft. So we usually use a predictive type of maintenance just to make sure that, a preventive type of maintenance just to make sure that they will not reach its failure rate. For it failed, we can just fix it or either replace it. Of course, the flight controls system are vital for safe aircraft operation, as we said. Control services such as ailerons, actuators, cockpit controls, these are all has to be taken into consideration in order to keep our reliability or increase it. Okay, now one of the major aspects or the major things that has a relationship between reliability is the quality. So in every, as you know, in every organization there is a quality. Quality is simply a degree to which a service or item can meet its standards. However, the product reliability is directly related to the product quality, which means if I am having a high quality in my organization, this will produce for me a high reliable components. But on the other hand, of course, if I'm having a low quality products, this will give me a low quality reliability, or even if I'm taking the product with having a low quality organization, this will decrease my reliability. So here in UAE, alhamdulillah, we have like a head in aviation in the Middle East with big operators such as the Emirates, Etihad, Air Arabia. So correct maintenance strategies, as we said in the RCM, will improve our maintenance impact to enhance operation reliability and cut the costs. This, of course, will give some benefits such as improving our operations, enhance reliability, and the cost reduction. So our suggestions, however, some of them is kindly implemented, but some of them still not implemented. Our suggestions to implement this in UAE as to have an internet app, softwares, send instant notification and task details, such as knowing when these components are near to the wear out zone, as we are using our preventive or the predictive maintenance strategy. Also, this will give us a tracking of the history of the components itself. Of course, this will prevent errors, duplication of the work, and delays in the crucial information, and this will also give benefits to our passengers and our customers. Aircraft maintenance software, as we said, tracks the all status and all the history of the components. So this proactive approach will optimize the maintenance, cut costs, and boost our aircraft reliability. So in conclusion, I would say that insightful exploration into factors affecting aircraft reliability, opportunities for improving identified for aviation operators and associated organizations. As we said, we have so many factors. Here we just address a small few factors that can affect the reliability. Of course, this is only a simple calculation. In our research paper, we made a lot of calculations and more in deep, but I don't want to, I have only 10 minutes, maybe 15 minutes. I don't want to waste your time, ladies and gentlemen. And that's it. This is my team. They were not being able to come here due to some issues in the work. But however, thank you for listening to me today.
To try and keep us on track, if I could ask, we give questions, so if you could speak to Mr. Hamdi after yourselves, I think that would be better. So if we just thank our speaker one last time. Now, I know we're running a little bit late, but I think it's important to have a break. I've been told if you are sort of wanting the break, don't go far. So we start the session
session in the seminar room this morning. Hope you're enjoying yourselves so far. It's a shame that it's only a 2-day conference and we're already on day 2, so that's time is running fast. So we're going to get started. We're running a little bit behind schedule, so we're going to try and make sure you have time for questions as well. We've got 3 wonderful presentations coming up this afternoon, or certainly this morning, on the topic of risks in autonomous aviation systems. And first up is Bartolomiej Żywonski, who is a PhD student at the Faculty of Mechanical Engineering at Wrocław University of Science and Technology. And his presentation is on the design of rapid response unmanned aerial systems for cardiac arrest victims rescue. So Bartolomiej, over to you. Thank you very much.
Thank you. So good morning, everyone. My name is Bartłomiej Żywonski, and I'm a student, PhD student at Wrocław University of Science and Technology in Poland. And I would like to tell you today about the design of rapid response unmanned aerial system for cardiac arrest victims rescue. And for starters, we need to say that the current problem that actually made us consider designing such an aerial system, and what are the goals that will going to make us achieve that purpose. Later we will do a quick state of knowledge part, so the review of the actually existing systems of such purpose, and at the end we will discuss our concept, both for the airframe and the whole system, and the summary of our project. So, what made us consider doing such aerial system? We done research, and it turned out that the main reason for deaths, both in Poland as in European Union and in the world, are the cardiovascular diseases. In Poland, up to 37% of deaths are caused by cardiovascular diseases, and more than 40,000 deaths out of those 37% are sudden cardiac arrests. It's about 40% of whole number of deaths caused by cardiovascular diseases. The average of the Europe is 38%, so it's also a big number. And the problem is, it's not enough rescue teams to let's say, go to the sudden cardiac arrest in the time that will make saving human lives possible, in the way that the victims will not have any neurological complications after such cardiac arrest. The average time in Poland for the rescue team to arrive to sudden cardiac arrest is around 14 minutes in urban areas and 21 minutes in suburban areas. And in some states we have around 4 to 5 rescue teams for the whole, we call it voivodeship, so let's say state in our country. After the 4th minute, after the cardiac arrest, the brain tissue starts to die. So basically after the 4th minute without proper CPR, the unrecoverable neurological damage start to occur in human brain. And this will be even worse. Why? Because the number of online jobs is still increasing, and we need to see that the main area where people where are the victims of sudden cardiac arrests is at home, actually. So where there is no auxiliary external defibrillator to be used, because number of AEDs is significant in urban areas, in city centers, at university or public transport. You will probably meet AED, but in suburban areas or villages around towns, you will probably not see a single AED. And the European Resuscitation Council guidelines strictly say that the main goal for saving people with sudden cardiac arrest is decreasing the time from the calling the help and the arrival of the rescue team. And that decrease can be achieved by implementation of unmanned aerial systems. So the goal of this project is to design the system, not only airframe, not only aircraft, but the whole system that will be able to deliver the AED to sudden cardiac arrest in less than 5 minutes on the radius of 8 kilometers. What are the current systems of such purpose? We have Everdrone, so the company from Sweden that is using the multi-rotor drone with the cruise speed of 83 kilometers per hour, where the AED is lowered on a rope. And it's actually the only one of existing systems that is implemented in real life. It works in Sweden, and it's actually saving lives already. The second system we met in our research is the Horizon from Germany. It's the only system for now that has a combination of the wing and multi-rotor design, so it's a VTOL, right? Vertical takeoff and horizontal landing aircraft. The cruise speed, as you can see, is significantly higher than for the multi-rotor design. The other one is the system where the drone is AED itself from the TU Delft, and the cruise speed is again lower than 100 kilometers per hour. And what is our concept? We decided to combine a flying wing design with the vertical takeoff and landing capabilities. So basically, we are going to use an airframe of a flying wing that is able to fly horizontally with horizontal leveled flight up to speeds of 160 kilometers per hour, so twice the speed of current multi-rotor system, because the tilt they need to achieve to move forward, they limit their own, let's say, horizontal ground speed. And our airframe will be able to transit from horizontal flight regime up to vertical flight regime and be a tail-seater that's going to sit vertically on the ground. Our AED will be dispatched from a special space in our hull and in airframe and lowered to the ground on a rope. We actually made a low-scale demonstrator to be sure that our design is doable. And how the system is going to work. We decided we will propose our National Research and Development Agency that we will do a circle of few systems of such purpose around the city. So basically, we will cover the all suburban areas of city up to 500,000 population with 7 to 8 drones, each that could work on the radius of 8 kilometers. And because of cruise speed of 160 kilometers per hour, the victim up to radius of 8 kilometers can be achieved in 4 minutes. So we will land at the time when the neurological damage starts to occur, to be sure we can deliver help in proper time. So the stage one we are discussing right now in this presentation is the design of aircraft itself. So development of an airframe, the aerodynamic design, and also the design from the perspective of flight dynamics. In this stage two, that's actually going to start in December of this year, we will work on the airframe itself. So we will build the airframe, the landing site for this drone, and we will also test all those components in laboratory conditions. So up at the end of stage two, we should have technology readiness level of 6 with our system. And to the design itself, the takeoff weight estimations were the most crucial ones for us. Why? Because we have the drone that has to fly vertically, holding 15 kilograms of weight, because that's the preliminary weight of our airframe with AED inside. And later on, we have to be able to achieve cruise speed of 160 kilometers per hour in horizontal flight. So our propulsion system, both engine and propeller, need to be able to generate more than 15 kilograms, actually almost 30 if you consider safety margin of 2 for hover, in the vertical flight, and later the same propeller, without changing the angles of propeller, need to be able to achieve the thrust required for horizontal flight in the horizontal flight. So we're talking about 30 kilograms of the static thrust and at least 5 kilograms of dynamic thrust during the flight. It's not so easy to combine those two parameters. And with our wing tube loading, we will achieve values around 13. So that's going to be aircraft that is flying on high Gs, up to 8, 9 Gs. We analyzed several electric motors. We took into consideration of also internal combustion engines as well as hybrids, but the best performance in terms of weight of the whole propulsion system and also the best performance from the perspective of the energy performance. So up to 8 kilometers of radius, we're not so much interested in internal combustion engines or hybrids, because up to 8 kilometers we can use fully electric aircraft and it's not going to be a problem for us. Later, we've gone through aerodynamic analysis. Why is that? It's also because our aircraft needs to be dynamically stable, both in hover and in horizontal flight. So we need to have center of gravity in the exact correct place, not only in, let's say, for the pitch and roll characteristics, but also in directional axis. Our center of gravity needs to be perfectly correct, because if not, in hover, the thrust from the two motors we have will make our aircraft unstable in hover, and we would be not able to lower our AED to the ground in proper time or to the victim. So we evaluated our airframe in terms of the lift, the drag, and also the stability in all three possible axes. So the lateral, longitudinal, and directional axis for both phases, which are hover and horizontal flight. And here you can see the preliminary 3D model in CAD software. I believe in the article in the conference proceedings you can see more detailed designs, so I encourage you to see our paper in proceedings. And what will be the scope? The last stage, so stage 3, will be testing of such system in real life. So in 2026, after the stage 2, which is the laboratory testing, we will be flying for more than 7 months in winter, in spring, and also in summer, to be able to test our aircraft in multiple weather conditions and see whether the design is suitable for the goals we established in the proposal for our National Research and Development Agency. So as you can see, the stage 3 is the testing not in laboratory but in real life conditions. So the project should end in August of 2026 with technology readiness level of 7. And I would like to thank you for your attention. I tried to make it quick.
Ramesh, thank you very much. We've got time for just one question. The presentation was so perfect that there are no questions, but I'll ask one question. Obviously, one of the biggest challenges in terms of getting regulatory approval is to make sure that the operation is safe in urban areas. Have you got plans for that?
Yep. For the TRL7 testing, we will fly in suburban areas, but in terms of urban, we are in talks with our local civil aviation authority, because for such flight with such system, so 15 kilograms while flying 160 kilometers per hour, we will need they need to agree to fly in, let's say, special mission profile. We implemented the multiple LiDAR sensors on board this aircraft, as well as two cameras that will be equipped with image recognition to allow us to avoid, let's say, critical infrastructure like electrical lines, bridges, or railway tracks. However, the stage where we are avoiding the high buildings, or we are able to maneuver through the city centers, is still to be discovered. However, we have an idea for this, to implement the let's say, static approach tracks. So basically, there will be a map of the city center of a big city that want to implement such system, and before implementing this system that will fly autonomously, we will need to fly it manually with pilot to establish approach track lines. Let's say, like, I can't say ILS, but there will be the uncovered track for this system to approach victims in certain points in city center before implementing. That's the idea for now, but I'm sure when we will reach TRL7, we will think of going further.
Okay, well, to get to TRL7 in less than 2 years, I think is impressive. So well done. Okay, thank you very much, Bartolome.
Thank you.
Thank you. Next up is a talk on pilot shortage problem solving with extended minimum crew operations. And the presenter is Captain Khalid bin Sultan. Khalid is in the room. Oh, you are representing Khalid. Okay. Well, in Khalid's absence, I will introduce Khalid. Khalid is a captain working for Emirates Airlines. He is an Airbus A380 captain, and he is marking his 20th anniversary at Emirates as a pilot in about 2 months' time. And he has the special claim that he was the captain of the first Airbus A380 demonstration flight involving 100% sustainable aviation fuels. But you are representing Khalid, so thank you.
Thank you very much. And Khalid sent his best regards to all of you. And he has in duty, he is a captain of Airbus 380 and now flying with the Airbus 350. Which will be the brand new challenge for Emirates Airline. I am very lucky, he is my colleague, and we work together in this project, and we would like to introduce the single piloted operations. In this morning, Captain Sebastian Hall, Boeing 777 captain, also presented the same presentation, but different approach. I will show you another approach, and really hope you will enjoy. All right. This is a revolutionary things. This is a brand new story. We saw many revolutionary things in our life, in aviation, definitely. Some is visible, some is invisible. So, for instance, when I was young, and in 1989 started in aviation, there was four crew members on board of the aircraft of the Russian technology, which means there was a captain, the co-pilot as a cabin crew, and also the part of the cabin crew was the flight engineer and the navigation officer. So 4 of them are flying in the cockpit, and they help each other, definitely. But at that time, in 1980 and 1990, there was a revolutionary technological impact, and they introduced the flight management system and the flight warning system. It means we don't need anymore at that time for crew in the cockpit. So the flight navigation officer and the flight engineer retired. So we have 2 pilots now. But if you look at the future, we have some problems. We need more pilots, we need more staff, we need more crew, not even cockpit crew, but also cabin crew as well. The reason is very simple. Look at for instance, Dubai Economic Agenda, Dubai 33. The vision is very clear. Dubai must be the 3rd most important city in the world, minimum the 3rd, if not the number 1, in the world in terms of aviation. Now Dubai Airport is in terms of international flights, international passengers, is the biggest airport in the world in terms of international flights and passenger. It means the London Heathrow, Amsterdam Schiphol, or Charles de Gaulle in Paris, they are behind Dubai. Dubai Economic Agenda also introduced, it must be double-sized the economy of Dubai within 10 years. And it will come as the single piloted operation. My name is Sipos, so that's why we're always joking this is a Sipos technology which we've introduced. That's why I am representing Khalid regarding this. Okay, if you look at the increased demand of transportation, everybody knows there will be 10 billion passenger is coming within 20 years. It's not an ambitious plan, that is the fact. So if you look at this diagram, it shows very well if you want to grow in terms of aviation, you want to have more flight, more passengers, more cargo, definitely, because we are always talking about passengers, not talking about the consigners. The pilot shortage will be a challenge. According to the Boeing and Airbus, we need 585,000 pilots, or nearly 900,000 cabin crew within the next 2 decades. So it means we need more staff who is going to fly, who is going to operate, who is going to maintain, who is going to control, who is working in this industry. Okay? So, and the most affected region is the Middle East. How can you fix this? How can you fix this? There are plenty of options. You can raise the level of the age limit of the pilots. It happened by ICAO in 2005 or 2006. I was there at that time, and we raised the limit from 60 years to 65 years. And of course, more pilots can work. But this is only one option. There are many other options. You know, you can utilize the pilots much more with the flight hours, and you can have a better plan. But also, you can do, you can do with a single piloted operations initiatives. These are very complex issues. It's not easy, okay? But nothing is easy, but it will come. There are many factors: human factors, technological factors, regulatory factors, financial factors. If you and many things. Only just financial issue. In the United States, this new initiative every year can save for the airline more than $8 billion because of they reduce of course the income, reduce the salary and the other extra things which we has to pay to the pilots. You know, if you reduce the number of pilots, it means you don't have to pay much more. Technological impact, seems easy, but it's very complicated. Don't forget, these pilots, it not means only one pilot is on board. It was mentioned this morning by Captain Sebastian. There are 2 pilots on board of the aircraft, definitely. One pilot is controlling, we call this flying pilot, and there is a pilot who are in rest, okay? The rest means during the cruising level. So cruising level means when you reach the altitude, the cruising altitude, till that two pilot operations, but after the cruising altitude when you are on, of course only one pilot will control the aircraft. And during this period of time, the other pilot is resting and not inactive of the operation of the aircraft. Of course, during landing, there is also, the other pilot will help and support each other. All right, we are going to about SIPOS, I mean the single piloted operations, but now this is another phase. This is the end of phase. Now we are in the extended minimum crew operations system, which was initiated and supported by Airbus. And of course, as you can see, the pilot is resting. That means the pilot is sleeping all the time or reading books or whatever. They are very active. Now we have dual operation, two pilots on board. They check each other, they help each other, they support each other. And that is one of the great big risks, because that one piloted operation has a lot of technical, procedural factors which we have to rewrite, reorganize, and rethink for the future. All right, what does it mean? Look at the situations. If the pilot has some problem, one pilot is in resting, the other pilot in controlling the flight, there is a fire. For instance, pilots are fearing from doctor and from fire. That is the most important danger for them. If the fire is coming, how you can react? How can you, of course you have to inform your colleague, but it is a lack of time. You have to react immediately. You have to, if you have an unconscious situation, medical problem, you have to do something immediately. But the other pilot is not in charge, is not in controlling the aircraft itself. So there are a lot of things we have to solve and we have to think for the future. Because now they help each other. Now if you look at the checklist, if you look at the emergency situations, the two pilot has a very important task. And this task is divided, they control each other on the top of that. But in this situation, when you have to react immediately, you have no time to wake up the other pilot, and even, and according to the survey, if you wake up from a resting position, you need not 1 or 2 minutes what we think in the real life, but when you are in duty, when you are responsible, you need 50 minutes while you are fully wake up. It takes time, but we don't have time. So that kind of procedure must be rethink and supported by the technological impact to achieve these wonderful initiatives which was launched by Airbus. Look at the risk and challenges. Pilot incapacitation is, we are not thinking about the pilot in bodily injury or death, no. We are thinking about lost the conscious. When the pilot lost the conscious, the other pilot, how will realize this? How will take into account what they have to do? So that kind of things must be organized and must be controlled and checked. Cross-checking information procedure and loss of pressurization situation. If you lose the pressurization, you have to descend the flight immediately for 10,000 feet. It takes, you have to do immediately, but you know, now the dual operation, one pilot is talking and connected to the air traffic management. You have to inform the air traffic management about your flight position. The other pilot is, of course, doing the action. And also in fire, one pilot is doing the action, the other try to fix the fire and try to follow the procedure according to the airline protocols. It was mentioned this morning, one of the biggest factors which is against this new technology, which will come. I will tell you which will come. We cannot avoid that, as we cannot avoid the flight engineers disappeared, the flight navigation officer disappeared. One of the things is the passengers. And also, if you look at the trade unions, IFALPA, for instance, International Federal Pilot Association, they are against these initiatives. Airlines are hesitating, because as I mentioned, airlines can save money regarding this. And if you remember yesterday with the keynote speaker of IATA representative said the airline's margin is very low, only $6 US dollar per passengers. Of course, the money is very important. The income, the revenue is crucially important to airlines. So if you look at, we make a survey, we sent out for many professional people and those people who are not working in the industry, what do they think about this new initiative? How comfortable with this idea? And if you look at the results, it shows very well. You cannot say something is very high, something is very low. It's a decent. It is average. So there are a lot of people supporting the other way, and a lot of people unsupporting. Some of them they don't believe it will come true. Some of them they believe it come true. And we look at very carefully the young generation, the older one, of course, educated, uneducated, working in the industry or not working in the industry. So we realize this kind of initiative, it needs more time to meet with the interest of the passengers, of the public. Definitely that was our result. Yes, before I just close my presentation, thank you very much for your attention. You have to understand something very briefly. I have 1 minute more, or we run out of time?
1 minute, yes.
Oh, thank you very much. Only 1 minute. There are, as I told you, it's not only technical issue. The technology is ready. We can do it tomorrow. And one way we can do it without pilots as well. It will come. Definitely look at the intelligent highway or the robot technology. But one of the big challenge for, if the pilot commit mistake, if the pilot cannot follow properly the procedure, and there will be a catastrophe because of that, or there will be some accident coming, that the air carrier will be liable. So the air carrier, because the crew has no legal relation to the passengers. The crew has legal relation to the airline. The airline legal relation between the passenger and consignor. So what does it mean? It means the air carrier and the aircraft manufacturers, they have to be very careful how to build this new system, because the responsibility on their shoulder. Thank you very much, and wish you the best.
Okay, again, just time for one question. Again, another perfect presentation. Almost. No, you got to stay here. We have one more question here. So.
Thanks. So my question was, we moved off the navigator and also the flight controller out of the cockpit because there was technology, right? We could kind of replace that with a weather radar, in-flight radar, all those kinds of things. So are you seeing that currently also there is technology with the aircrafts, with the airlines to reduce the amount of pilots in command or the pilots in the cockpit? And rather than perceptions, is it feasible? Like, that's one question. Is it just being held back because of the perceptions, or is it because of the infeasibility that we are kind of holding them back?
Just tell me again, please.
Okay, my question was, we moved out the navigator and also the flight technician out of the cockpit with technology.
In the past, a long time ago.
Yeah, with the technology. We had those advancements in the technologies that made that move. So are you saying that we currently have that technology within the aircrafts, within the aircraft manufacturers and the airlines to move out a couple of pilots, operating pilots from the cockpit? And is it just that it's being held back because of the perception-wise?
Yeah.
Or
yes,
is it just...
Definitely, it's very complicated because, as I told you, look at the emergency procedure for firing, 8 pages only the checklist. Yes. Somebody has to read that somebody has to action, and there is no time. Every minutes are count, definitely. I think as I said, the technology is ready. They have to find how with of course the aircraft manufacturers and air carriers, how they can put it in the real life. It will come, definitely, believe me. It is ready, but there is no regulatory background for this. There is no social background, and because who wants to fly without pilots in the future. Thank you very much.
Thank you.
Thank you very much. I guess the current modern cockpit is designed for two-pilot operations, so there'll have to be a radical change in the physical layout of a cockpit to enable single operations, but incredibly interesting, so thank you very much. That was a great presentation, and we move on now to the final presentation in this session, and that will be delivered by Maris Goloskis. Maris is a second-year master's student in intelligent robotic systems. He's a robotics engineer and a researcher at the Riga Technical University. So, Maris, over to you. Thank you.
Thank you for the introduction. Hello, as he said, Maris Goloskis from Riga Technical University in Latvia, and I will present the results from our paper, Risk Dynamics. I'm not the main author, unfortunately, but I'm sure I will convey the idea pretty good to you. Yesterday I heard a joke about the last presentation before lunch and thought that, yeah, unlucky, but yet here I am today, and the previous two speakers took all the time they have. So let's jump right into it. So what hides behind this rather poetic title? So, as we look forward to 2023, urban air mobility is expected to grow exponentially, with predictions suggesting a tenfold increase in drone flights comparing to today. It is estimated that there will be around 68,000 UAV flights per hour over the area of 12,000 square kilometers. It is an equivalent of about 10 flights per hour per square kilometer. So it is not that much, but still way more than today. There are no real traffic management systems as of today, so everyone is either flying alone with the whole airspace blocked for other drones, or there are no real type of management for them. For the air traffic to be considered safe, it is expected the fatality rate should be below 1 fatality per million flight hours. And by fatality, it's not meant a crash. Fatality means there has to be some injury to a human. So since there are no humans on board of a UAV, a crash is not necessarily a fatality, since it has to fall onto a human underneath. So to test out where the possibilities of danger could arise, we created a simulation. So in the simulation, each UAV is defined by 4 parameters that are in the range of commercially available drones of today. So it's the aircraft dimensions, maximum flight speed, maximum flight time, and flight speed, that is the nominal flight speed that the UAV would take whole of the journey with. And there is defined this rings of sensing, and it would be necessary for the UAV manufacturer to equip the drone with sensors capable of sensing other things in the air for the 10 to 20 seconds ahead of the journey. So if the drone is capable of flying super fast, then it would be necessary to equip it with more expensive, more capable sensors. The world is, the environment is designed as follows. There are 4 scenarios. Uniform scenario when there are no additional variables. Then there are these higher density zones that would be representative of a higher area, or higher density areas in cities, for example, more populated areas. Then there are these no-fly zones. I'm quite sure you know what they are. And then there are scenarios with both higher density and no-fly zones enabled. There are 2 airspace organization strategies. One of them is when the drone is assigned a random flying height, and another one when they are grouped together with the same heading direction, therefore minimizing the risk of head-on collision and a collision in general. And there are 2 flight level heights. One of them is 10 meters, which corresponds to today's standard of vertical resolution, for example, GNSS design systems, and 0.1 meter is a future system that would be necessary to actually improve things. Here we can see visualization of all 4 scenarios. Actually, on far left there is when nothing is enabled, and the bottom right is when both zones are enabled, and the UAVs have to fly around the no-fly zones. Let's go to the results. So as we can see, heading random when the flight heights are smaller, the dispersion of drones in the airspace is better, and therefore the risk of collision is smaller. And the heading height is the grouping of drones from the flying direction that also improves things when there is this uniform scenario with nothing considered on the ground. But it's not a real world scenario, so let's move on to the no-fly zones enabled. And when we enable no-fly zones, there is a steep increase in the collisions per flight hour. As you can see, before it was more about 0.01 collision per flight hour per square kilometer, then here it starts already at 0.05. When we enable higher density zones, we still can see that heading height is better than no heading height, but the difference between heading height and just random height assignment is smaller. Why it's so a bit later. And when all zones are enabled, there's this thing that for the first time ever, random heading height is better than any kind of arbitrary assignment of the heading height. So, what we found out. Results indicate that there is a clear advantage in using smaller heading height, smaller flight levels than 10 meters. But for that to be possible, there needs to be advancement in sensor technology. And to mitigate collision risks around no-fly zones, they have to be used as least as possible. And in evenly distributed area, the heading height strategy clearly gives an advantage over just a random height assignation. Here is a small visualization of collision densities, and when the no-fly zones are enabled and there are no smart ways of flying around them, there becomes a congestion around the no-fly zones, and the collision risk is really, really high. So, in the future, we are planning to improve the simulation by adding advanced path planning, refining the collision avoidance algorithms for multi-drone scenarios, and enabling active collision avoidance whatsoever, because here there was no collision avoidance. And we plan to include uncooperative UAVs that would represent someone who is not authorized to fly. Therefore, the autonomous drone should create a bubble of safety around this UAV. Thank you.
Maris, thank you very much.
Do you have any questions or lunch? Oh,
okay,
please.
So I have a question here.
Thank you so much for the presentation. I'd like to ask if the data you have worked on was from Latvia. Oh.
Thank you. Not necessarily, but the area that you saw on, let's keep it here, with the higher density zones and no-fly zones, it was from the Riga, yes.
Okay, so the reason I asked this question is because when it comes to the Middle East, one major challenge is heat. So please correct me if I'm wrong, like the LiDARs and other sensors are very temperature sensitive. And when it comes to heavy deployment of drones in the Middle East, will this pose a challenge, or you feel like the current technology of drones or UAVs, eVTOLs, is good enough to overcome this challenge of heat?
Thank you. To be fair, this research doesn't really look at the hardware for the drones, but in my opinion, there has to be some advancement, but I think that the technology is there, but it maybe could not be, it's not affordable enough to be mass produced and put on all of the drones. I hope this answers your question.
Yes, it does.
It is there, but
because if the sensors are malfunctioning because of heat, there will be collisions because they are not mapping the real world environment around them.
of course.
So, like, could you please shed some light on the relation of collision with inaccuracies due to external factors?
I'm sure we'll look on this in the future research, but right now I can't really answer you.
Thank you. Thank you. Helps.
Frank, I think there's quite a lot of variables that go into
Yes.
the collision metric, right? So what you've done is you've simplified the approach in terms of the research, but that gives you the opportunity, the platform now, to add more variables and do that collision analysis.
Exactly.
Okay, I think there was another question. Same question? Okay, thank you. Okay, that brings us to the end of the second session in the seminar room today. I think we are a little bit ahead of time now, having fallen significantly behind time. So we've got the next session on leadership and training in aviation is starting at 12:20. We have 2 presentations and then we go into a lunch break. So what we'll do is we'll have a short 5-minute break now, time to stretch your legs, maybe grab a coffee at the back of the room, and then we'll return again in about 5 minutes' time for the final session before lunch. Okay, thank you.
ladies and gentlemen, we are going to continue our journey. And today is a very special topic we have. One of the most important in civil aviation is the training, education. If you look at the annexes of the Chicago Convention, the first annex is the personal licensing. That is the alpha and omega, how to teach, how to train, how to build the future. And today our topic is of course, the leadership and training in aviation. Our first speaker is Dr. Evangelia Pantalaki. She is coming from the Faculty of Business Management and Emirates Aviation University. Dr. Evangelia Pantalaki is a senior lecturer within the Faculty of Business Management at Emirates Aviation University, Dubai, in the UAE. She is an economist, and her research interests are sustainable aviation, business aviation, leadership in airline companies, and aviation and tourism. She has participated in applied research projects in Italy, in UK, and also she has worked with UK local authorities and UK's Department of Transport. She is a reviewer for highly ranked peer-reviewed journals and sits on the editorial board of Research in Transportation Business and Management, Journal of Air Transport Studies, also Journal of Airline Operations and Aviation Management. I take the floor to her, and please share your knowledge with us. Thank you very much.
I want to see how this works. Okay, can you hear me? Perfect. Thank you very much, Attila, for the nice introduction. And thank you very much for being here in Emirates Aviation University. The topic that I will present you today is a joint work with Professor Andreas Papatheodorou from University of the Aegean in Greece. A little bit about the topic and why we selected this topic. Actually, there was a call from Professor Gil Oman and Dr. Bozanas Passogevis from the University Griffith in Australia, and this is an extended work of a book chapter that will be published in March 2025, so in a couple of months. So I will be talking about the leadership in the airline companies, and we will compare what happened with the CEOs of the airline companies before, during, and after COVID-19 pandemic. This is a typical outline of the presentation, a background, the motivation of our study. I will discuss a little bit about the academic literature and what is the evidence there. I will describe the methodology that we used for our analysis, and then I will conclude my presentation with some key results, policy implications, limitations, and of course, future research directions. So everyone now knows what it means COVID, and especially for aviation industry, it was a huge hit. Between 2020 and 2019, we saw a 60% decrease in the air traffic, which is translated in 2.7 million passengers less, and of course, losses for the airline companies of $372 billion. What was the consequences for the different levels of employees in the airline companies? I'm focusing only on the airline companies' employees and not in the aviation industry in general. Here you can see on the one side a pilot that he changed his career during COVID, and he started working at the COVID-19 testing site. On the other side, you can see a cabin crew that she decided to turn her hobby into a business during COVID, and although she enjoyed her job, she was waiting for COVID-19 pandemic to pass in order to get back to her work. On the one side, we have pilots and cabin crew that changed jobs or decided to do other things, but the airline CEOs had a different response. What they did, we can see some news from professional magazines and newspapers that they have taken pay cuts for their salaries and their compensation. And we need to consider that their pay cuts didn't have a huge impact on the profitability or the losses of the airline companies. In any case, the companies were already having huge losses. And this was an indication of the empathy that they wanted to show for the, in general, bad situation for the airline companies. So what is the aim of the study? We want first to identify and compare the pay cuts during and after COVID-19 pandemic. And we want to see whether the publicity of this measure has actually impacted the employees' morale and the empathy that they wanted to show. Let's see what the academic literature shows about this topic. First of all, we need to identify what is a leader, and I'm quoting this from Napoleon Bonaparte about the definition of a leader. It is actually a dealer in hope, and it shows that his role is vital, and the role of leaders is very important in order to show, to empower the employees, and especially in uncertain conditions like COVID-19 pandemic. In this slide, you see that the organizational performance is getting input from the corporate strategy, but also from strategic leadership. And corporate strategy and strategic leadership have a bidirectional relationship. The one feeds the other. And researchers that studied low-cost careers in Thailand found that the high competence personnel, so we're talking about senior managers, they scored, these characteristics scored the highest percentage among other important factors in the performance of a company, like the organizational culture, risk management policies, and any human resources management. So the literature shows that the leadership is quite important for the performance of the companies. And the leadership is preceding the internal marketing and the external marketing. So what do we mean by internal marketing? We mean any policies for the employees, like training, rewards, promotion schemes. And external marketing refers to customer satisfaction and, of course, customer loyalty. And the leadership is helping the employees to be active, motivated, and want to contribute in the company. And this has an impact, of course, on the customers. So the happy employees can also satisfy customers. And as Richard Branson says, companies should put employees first, exactly for this reason. More scientific research, I will not focus much on that, but briefly to mention that the leadership theories that have been applied in the airline companies are very few, and still we need more research on that. The different leadership theories have studied the impact of leadership on employee satisfaction, service performance, employment commitment, safety climate, counterproductive behavior, safety communication, team efficacy, and also crew resource management practices. And this type of characteristics have been studied both in flight attendants and other employees in the airline companies, like pilots, transit and check-in employees, baggage services, which shows that the leadership has an impact in different roles in the airline companies. Let's move on now to the importance of crisis events and the management of crisis events. There are 3 stages. The first is the prevention and detection. So we're starting before even the event, the crisis event. We need to have a plan and explore the different factors that can create a crisis. We need to create also a management team for that and be prepared for the second stage. The second stage is when the crisis actually happens, and then we need communication. It's very important. We need to communicate the process to the stakeholders, but also to the employees. And finally, the third stage of a crisis event, it is the post-crisis actions. And what we mean by that, we still need to communicate and have a plan for recovery. In aviation, we can have different crisis events, like, for example, unruly passengers. We can have either very difficult weather conditions that can impact the performance. So let's move on to the methodology and how we did this study. It's very difficult and challenging to get information from the airline companies themselves. So what we did is that we searched in the different publications from professional magazines online, and we saw what the news say about the CEOs and their salaries. We didn't focus on a specific geographical area because we couldn't have so many data to analyze. And the methodology that we followed is a pre-post study. We saw what were the levels of the CEO salaries before and during the pandemic, and then we compared them with the after levels. Wow, a little scary, eh? Okay, let's see now the numbers. Is the table visible? Can you see that? Okay, so I have highlighted with red boxes the most important information. First of all, let's see how generous the CEOs were with the pay cuts that they received. First, starting with the Air New Zealand, the CEO accepted a very, very small percentage, only 15% of his compensation. Then another situation is from Singapore Airlines, where the CEO decided for a small pay cut in the beginning, but as COVID situation was worse, he accepted more and more pay cut and reached until 35% of his total salary. Other CEOs were more generous from the beginning and have accepted 100% pay cut, which means that they didn't receive anything at all. But we don't say that we need to read behind these lines. The salaries of the CEOs have the base salary, but also they have stocks, they have pension schemes, they have extra benefits. So for the sake of publicity, mostly when we're talking about these numbers, we're talking about the base salary, but not all the other advantages that they have. In the case of the Qantas airline, we see that the CEO accepted 100% pay cut, but then he thought it's too much, so later on he accepted only 65%. And in most of the cases, the pay cuts were for very short periods, okay, not very long periods. Let's see now what's happened after COVID pandemic. When we say after, we consider years 2021 and on until 2023. This is what we call after. The airline companies in the United States see the salaries of the CEOs to increase, and they increase also substantially. So mainly in the United States, the CEOs have higher salaries compared to the pre-pandemic levels. And the highest paid CEO is the CEO of Delta Airlines, which is 34.2 million. And then in Europe, the highest paid CEO is the CEO of Virgin Atlantic with 4.66 million. And also the CEOs of Air France-KLM with 4.66 million again, and the CEO of Lufthansa with 4.6 million. We have also a CEO that was not that lucky. It is the CEO of KLM that he has also a decrease before COVID. So before COVID, his salary was 1.4 million, and after COVID, 765,000 euros. Well, these are actually the description of the results, so I will skip these 2 slides. And let's see, what have we learned? Actually, were these pay cuts enough for the employees to continue their work? Actually, many of you might have faced this situation with delays, with luggages being lost. And why this happened? Because many people left the industry during COVID pandemic, and we have also shortages and strikes of people after the reopening of the borders. So the salaries, the pay cuts of the CEO salaries were not enough to show the good example for the employees. And this is happening both in the United States. These are all images from US airports, but also in London Heathrow. 1 year later, after the summer 2022, we see that still the industry hasn't fully recovered, but this recovery is uneven in the different regions of the world. Especially the UAE is an exception, as the industry has recovered more, substantially more compared to the pre-pandemic levels. And more complaints and more strikes also from flight attendants and pilots. The flight attendants actually in the United States were complaining about the increase of the salary of the United Airlines of Scott Kirby, that he recorded 90% increase between 2022 and 2023. And on the other image, you can see also the pilots in Mexico complaining against for the increase of the salary of the CEO. Conclusions. So the COVID pandemic was a very challenging exercise for the world, and especially for the aviation industry. And although the research has shown that the effective leadership can be a stimulated factor and can empower the employees, actually we saw that in aviation it didn't work. And the uneven recovery of the compensation of the salaries of the CEOs compared to pilots and cabin crew shows that there is a lack of empathy between them. So, before going to your questions, I want to stress that we have some limitations in this study. First of all, we use data that were only available on different articles that we found online, so we don't have official information. And also the pre-post study, so this type of analysis that we did, is not considering any other factors that can intervene in the relationship between the 2 variables of interest. So what are some key takeaways for future research? We could consider what is the difference between the salaries and the pay cuts between low-cost and full-service careers, and see if there is a difference in the business model. We can either move further and do a study about the employees' job satisfaction and the company performance that has been affected by the CEO's pay cuts. And finally, it will be interesting to see whether the different forms of government support that the airline companies have received has also an impact on the decision of the leaders to take specific level of pay cut. I have 2 or 3 slides with all the references. And this is my presentation.
Thank you very much, Dr. Evangelia Pantalaki. Do you have any questions, please? COVID-19 is crystal clear. Definitely. All right. Thank you very much, your support, and thank you very much, and congratulations with the book, Edgar.
Thank you.
Very good.
Thank you.
Welcome. All right. The next speaker today in the Leadership and Training Aviation panel will be Dr. Gerasimos Kontos. Dr. Gerasimos, welcome. leverages hands-on expertise on broad cross-functional knowledge across the air transport industry, including airlines, thank you, airports, service providers, and training. I'm not reading all, believe me. But
I believe you ring the wrong person.
This is aviation. This is aviation. Welcome. And he's a very special man because he's strongly believing in people development and their potential. He was awarded a Fulbright Scholarship for scholarly research on human factors and skills determination in the age of automation from San Jose State University, Department of Aerospace Engineering. His research focused on identifying the technical and non-technical skills required from flight crew and aircraft maintenance personnel to excel the challenges set by automation and digital transformation of the aviation ecosystem. Result of this research were recently presented at a joint conference organized by IFALPA and the UAE National Air Accident Investigation Unit. He has a very lengthy CV, very lengthy, but what we have to know about him as well, he's also, he acts as a director of flight simulation lab, where a range of simulation software are used for student training and experimentation like Explain and Pet Pilot gas turbine simulation. I give the floor to him, and thank you very much for your presence.
Thank you very much. And I'm Gerasmos. I come from Greece. Previous beautiful lady comes also from Greece, although this was not disclosed, but I disclosed it for her. I'm a professor of aviation at Abu Dhabi University, and my research mainly focuses on how you can use flight simulators with an educational perspective in a university level. And we do this usually for our students, but sometimes we also invite colleagues from airlines to test our system and see how they can work together. So, since it is a presentation before the lunch, we'll make it super fast for all. So, the majority of you know that despite all the technological improvements and whatever investments we do in technology and automation, still we have several aircraft, I will say first incidents and then accidents, and the majority of them following the analysis, there is always a part of human, let's say, challenge. I will not say error, but I will say challenge. And this is, to my perspective, and to the research we do, it's because that, you know, the more we try to automate the procedures, and we do this because we want to make sure that people will not, let's say, make any challenging decisions or any mistakes during difficult situations. So the more we rely to automation, the more the problem is that what happens when we cannot anymore rely and we have to, let's say, take manual control. This, of course, does not apply only to aviation. But to come to this topic, when the computers fail, and sometimes they fail, humans have to directly take control and understand first what is the problem, what the computer says it is the problem, and then to, let's say, take manual control and, for us, fly the aircraft. And as I said, the more we automate things, the more challenging it becomes. The good thing is that international organizations like the ICAO, IATA, EASA, and other organizations that directly try to understand human performance in difficult situations, part of the regulations, I mean, started to invest in training programs known as evidence-based program. What does it mean? It means that we train people in using realistic scenarios. So we try to imitate how they will act in a, let's say, simulated case. We monitor how they act in this case, and then we take some performance measures and we try to adapt the training on it. And in order to do this, we need to have, let's say, a base, a solid foundation, a framework. And for this, they have found out that there are 9 basic, let's say, flight competencies or pilot competencies that are required to be able to understand human behavior. And when you understand the behavior, then you can provide, let's say, training perspectives on this. And these are the 9 competencies, okay? One is missing, which is directly the integration of it, but you have the blue one are more technical oriented, directly related to how you are familiar to fly the aircraft in technical procedures. The, I'll say, not red, but light red or orange is the more soft skills perspective or less technical skills which directly relate to human behavior and how you react with your team in a cockpit situation, okay? So you have communication, and this is a description that says demonstrate effective oral, non-verbal, and written communication, and you can read the rest of it. Among all these 9, it said, but 9 is the integration, the most important knowledge is at any given moment to be able to familiarize yourself with what is really happening and what is the real problem, known as situational awareness, and which actually the ability to understand all the information provided from your environment, including the machine you have in front, and try to understand what is really happening. The good thing for us is that we have flight simulators, more expensive one, like that you found in the airlines, less expensive one than the ones that you have at home, using some software that you can use and in a desktop computer, like Microsoft Flight Simulator, Explained, and other flight simulator software. And what they do is actually they try to imitate how the aircraft will behave based on your reactions. The more expensive the machine it is, the more realistic it is. Of course, as you understand, the moment you enter the simulator, you already know that you will not, how shall I say, die, so no matter what you do, but research shows that whether you are in the real aircraft or in the simulated aircraft, your brain behaves the same, and this is a very solid foundation to using simulators. Besides the cost of doing it at home without having to fly the real aircraft. Now, what is the problem of this is that if you take 2 super experienced pilots, give them a same scenario to fly on a different classrooms, having exactly the same skills, exactly the same competence, even the same flight instructor, there is a high possibility that they will behave differently because there is a point known as human behavior and human skills and how you react on a different situations. To make it more simple, in a university class, not all students understand the same information at the same time. So training needs to be a little more, let's say, adapted to the student characteristic or to his willingness to understand the information provided. To come back here, from a pilot perspective, no 2 pilots are the same. Even if they have the same experience or even if they have the same training, they will react differently in a challenge not experienced before, because this comes to their own primitive characteristics. So, to make things more nice for us, we need to adapt the training to individual characteristics. And currently, this is the task of a flight instructor, which based on his experience and his own willingness, of course, to devote the time on this, he understands, based on the scenario on hand, he sees what the pilot does, he understands what he's going to do, and then he creates, let's say, his own personal profile. So our research comes to try to automate this. So we'll support a flight instructor to, let's say, make his life more easy by providing him or her some support on what is the profile of the candidate he's working with. And so we'll try to create a software that actually will pre-populate some flight training scenarios, meaning that he will be able to understand the pilot by monitoring his behavior, creating a profile for him, and based on his profile, he will actually identify what are his real needs on training. So he might directly go to the scenarios which are tough for him and skip the easy ones, making the train more convenient for him and more, let's say, also for the airline. In order to do this, the first thing is you need to have a standardized training language. What I want to say is that you need to speak, when we discuss about aircraft, everybody knows what is it. But when we discuss about weather or when we discuss about equipment failures, not everybody is familiar with these terms. So the first thing that we did is that we took the very super basic things that you need to describe a flight training scenario, super basic, okay, elementary school stuff. This is the aircraft. Okay, we use two types of aircraft, what is a Cessna and an Airbus A320. We use some basic aircraft characteristics like the payload, the fuel, the center of gravity, which influence the performance. We use some basic things of the weather. Again, I say elementary school stuff like cloud formation, winds, precipitation, visibility, not all the details that you will find in reality, because we need to first learn to fly and understand. We need the time. Of course, we use some geographic location for the aircraft, the position, and where the aircraft actually is. And then we started to model some failures, like either it is an engine failure or electrical system, fuel system, and the potential consequences. So we actually created a language, as you understand, a language that is able to describe all these things in a very solid and standardized framework. That was the first part. The second part is that we need to also standardize the scenario and how it will work. So we make three main classifications. We use events, which are unexpected occurrences that might happen. We use conditions, when this happens, and we use constraints. For instance, an engine failure during takeoff and an engine failure at cruise flight has a completely different procedure on resolving the issue. So we need to model this in the scenario, so we need to understand whether the pilot followed the correct process based on his training, or if he did not follow, we try to understand what was the mistake on it and try to solve it. So that's the base. Okay, so for instance, okay, we use a super easy example. This is a flight training, this is a part of a training scenario discussing about an aircraft takeoff and taking the procedure from the air traffic control to receive the clearance. And our framework is able to capture while flying all these characteristics. Okay, you have, as we discussed, the aircraft, the consequences, the weather, the performance, and what you see in the blue is actually what the framework is able to catch by monitoring the pilot while flying. So we take these blue informations while the pilot plays on the scenario. This is only for the takeoff, just as an idea. And based on this, we try to create a profile for the pilot and try to see whether he followed the procedure as part of his training or he deviated some parts. And then the most important part is that we model this then, after we finish the first part of the scenario, we model this in a flight simulator we have in our university, known as Explain. The majority of you may know it. And we try to understand and simulate what the pilot actually did. So we can have a, let's say, directly match between what is the real performance that we expect and what the pilot also did, and either it was correct or not. And at the end, we can also adjust as we proceed and we support our model to learn more things. We adjust also the training and we make it even more tough for him, so we are able to adjust failures in a real time and also change the performance of the aircraft in a real time. So this is, I believe this is the final slide, if not mistaken. Yes, so what is the benefit? Okay, we want to support flight instructors to make their life more easy. how we make their life more easy. We give them profiles of potential pilots based on previous data, based on previous training scenarios, and based on previous research that we did, that are ready to use, but they are missing some key important information. So we save him time and energy, and he can use, let's say, our system while he's sitting on a flight instructor in a simulator software, now only an academic version, of course, to be able to understand what is the real challenge that this pilot has and what is the real training need. Because we base our foundation that no two people are the same and, of course, behave the same on the challenge. Okay, that's it. Thank you very much. Okay.
Thank you very much, Dr. Gerasimos.
You know the cartoon Tom and Jerry?
No.
You know the cartoon Tom and Jerry? I am the mouse.
Ah.
So you can call me Jerry, okay?
I understand.
Yeah.
Thank you. We have time, plenty of time. Thank you very much. If you have any questions, please do it right now.
Yes, please.
Okay, thank you very much. I suppose that you have also modeling techniques or more statistical to show us.
Yeah, but we didn't.
You simplified this for this presentation.
We use some, I will not say intelligent algorithm, but we use some algorithms and data analytics to model the behavior in numbers and then to be able to add them in the scenarios.
Okay, very interesting presentation. My question is, are you considering any experience characteristics, like, for example, the flight hours or the age of the pilot, or as we see now more and more women also becoming pilots, have you considered any gender differences in this model?
First of all, that's a fantastic question, and thanks for asking. Yes, for now we keep it as simple as possible, just to be able to see how the model works, and then how to be able to see what is the real value created based on the data analytics. After that, of course, we need to I will not say separate, but we will include data about age, training experience, flight experience, gender for sure, and we can also separate it in different geographic regions that will support it.
Yes.
And of course, to support this, since we believe that no two pilots are the same, of course we need to also add differentiation characteristics.
Okay, my second question would be about the geographical area, because in some areas we might have specific accidents happening more frequently compared to other areas, like, for example, bird heats or weather conditions different. So you responded to that.
Yeah, yes. We are planning to also add geographic location. For current, because you only use 2-3 airports as a demo, you only use the real geographic location of the airport to be able to familiarize the flight path and the route of the aircraft. But after we proceed on the next scale, we will also add historical data from previous flights from different regions to try to model it. Okay.
Amazing. Okay, thank you.
Thank you very much.
Is there any question, please? Thank you very much, your presence. Thank you, everyone, today, the contribution. And please enjoy the lunch. And don't forget the next panels will be in the main room. And see you there. Thank you very much.
But still believe you read the wrong presentation.